Starting section 8.4 and 8.5 today, we're going to need your calculator quite a bit, so make sure you have that right out next to you. And we're looking at common logarithms in section 8.4. Common logarithm, a common log, is a logarithm to base 10. We've actually talked about the log button on your calculator automatically being base 10. So when you see just log of x, it's the same as log of x base 10. In the absence of a base, it's automatically base 10. So your graphing calculator, of course, has a log button, and the log button will return the common log of any number. So if we want to do the log of 5, and we'll do all of these, log of 72, log of 12.98, take your calculator, let me clear everything, and just do log of 5. It's good practice to close that parenthesis and then just hit enter. So the log of 5, is 0.69897000043, and it does keep going. It is not rational, it is irrational. But let's put down what we have. Go ahead and try ahead of me, log of 72. And you should have 1.857332496. And go ahead and try ahead of me, log of 12.98. So it's pretty easy. You're just hitting your log button. Now we have some special logarithms, and we've looked and done some of these in class, and we've discovered, for example, the log of 1 is, of course, 0. Consider putting this in Venn form if the base is 10, and I'm looking for the exponent. 10 to what exponent gives me 1? So, of course, that's 0. Log of 10, so 10 to what exponent gives me 10? And of course that equals 1. But go ahead and try it on your calculator as well, so that you're comfortable finding the common log of 10. Common log of 100, remember automatically base 10 here. Base 10 to what exponent gives us 100? Base 10 to what exponent gives us 1,000. Logs are exponents. So of course, 2 and 3. Confirm that on your calculator. So this very important relationship of changing something from log base b of a number, and remembering logs equal the exponent, into Venn form, base to the exponent equals a number. Very important relationship, really follows us all through the chapter. It's good to know. So knowing that, if we go revisit log base 10 of 5, and we know the common log of 5 was approximately 6,9. I'm going to round now to the thousandths, so that would be 90. This squiggly means approximately. Then we know, using our base to the exponent equals the number, that 10 to the 0.6990, let me write that a little bit nicer, should be approximately 5. So I want you to test this on your calculator. by putting in 10 to the 0.6990. And sure enough, you see that that's 5.0003455. Because we rounded, it's not exact. So remember from the beginning of the chapter, logs are exponents, and that the logarithmic and the exponential functions are inverses. We can see on our calculator, knowing that they're inverses, check out that log button. And check out what's right above it. If you hit second log, hitting the log button gives you log of something. Hitting second log sets up 10 with an exponent. So even your calculator knows that these are inverses. Okay? So if we want to do, or figure out the log of 24.6, just type that in. It's approximately 1.3909. So we know then that 10 to what power, switch this up, put it in Ben form. 10 is our base. 1.3909 is our exponent. So 10 to the 1.3909 should be approximately 24.6. And go ahead and try that. Maybe hit second log, 1.3909. And sure enough, 24.598, and you're set. So when you hit second log, you get 10 to the, and it sets you up for an exponent. Mine actually is blinking right up there like that. So the anti-logarithm is what happens when you use that second log, anti-logarithm. We're going to make a little sense of this when we're staring at these and we see a problem that says log base 10 of x equals 1.3492. You should know still that you've got Ben form to go to. So my base is 10, my exponent is 1.3492. But you can also know that if you're looking for the number, you can type in second log. So you really can handle this either way. I'm going to try second log of 1.3492. And I have 22.34601058. Round to 4 decimal places. 22.3460. Now, just as an aside, and this will help us down the line in trigonometry and in logarithms. If you have a question, log of x equals 1.3492, and you need to solve for x, the term anti-logarithm or inverse logarithm, we can write next to this log inverse. And right next to this, log inverse. So a log inverse and a log undo each other. I'm just left with x. And a log inverse ooh, that's terrible. Try that again. Log inverse means I'm hitting my second and my log button. So log inverse is a clue that you're going to use those buttons. And of course, second log of 1.3492 gives you the same answer we've already discovered. 22.34, rounding correctly, 60. So number 2, I have the log of x equals 0.2222. If I just want to solve for x, then I'm doing a log inverse, boom, boom, and doing a log inverse over here as well. Go ahead and type that in. Second log is what log inverse is, 0.2222, boom. And we have about 1.668015,185, rounding to 4 decimal places. That'll stay a 0. Go. Okay, let's do a couple more. Find x for this and find x for this. Maybe pause and try it on your own. Remember, in the absence of a base, it's base 10. And to do this one, I hit second log, log inverse, log inverse. All right, number 4, log inverse. To get x alone, log inverse of 0.1. And calculator, I get 1.258925412, and so that would be 1.2589. Again, thinking about this, I had 10 to the 0.1 equals what? And that's the same as putting in 10 to the or hitting second log. Okay, evaluate each log. So, wait, a little property review, possibly. Log of 27 minus log of 3. I'm going to say that this is the log of 27 divided by 3, which is the log of 9. Now, if it's base 10, I'm just going to hit log of 9. And I'm going to round right here. Number 6. Let's just type this in as it looks. Be careful to close that parenthesis. 3 log 5 divided by log 15. I'm rounding right here. Still doing those 4 decimal places. Okay, any questions? We can do lots more of these. We can certainly do a bunch in class as well. So let's do a little properties review here in the middle of everything, because these properties pop up all the time. So it's good to revisit them. Let's see. The log of 3 equals A, and the log of 5 equals B. So the log of 25 I could rewrite as 5 squared. So the 2 comes out front. 2 log 5. We're all done with properties, so this is 2, and replace it with B. Number 8, log of 45. Let's see, 45 is the same as 5 times 9, which is the log of 5 plus the log of 9. 9 is 3 squared. So I need the log of 5 plus 2 log 3. And now I can replace these with what they gave me in the directions. Let me scooch that up. So log of 5 gets replaced with b, and 2 times log of 3 gets replaced with a. Awesome. Log of 5 divided by 3. Remember this property? Log of 5 minus log of 3. Ready to throw in the b in place of log 5. Throw in the a in place of log 3. Okay, let's do one more of these. Log of 300 looks good. I know 300 is 3 times 100. And I know the log of 3 is one of my givens. So that's log of 3 plus log of 100. A plus, it's base 10. A plus 2 from the very first page of notes. Okay, if you want to do any more of these, we can certainly finish them up in class or try them on your own. Section 8.5 is about natural logarithms, more calculator work. A natural logarithm is a logarithm with a base e, and this is our special e value. Not e for exponent, but the special number. E is an irrational number. You find it on your keyboard, remember, on your calculator above the division sign and above ln. So it's approximately equal to 2.718281828, and it continues, but it does not repeat. So find on your calculator the ln button. Whoops, I'll show you where that is here. The ln button is right there. ln right underneath the log. You don't want to get them confused. The natural log and the common log are different bases. So let's try on your calculator now the ln of 4.13. Simply means you're going to type it in. ln of 4.13. And enter. And we see that that is 1.418277, etc. So we can write that in. Go ahead and try the ln of 10. ln of 10. Approximately 2.3025. Okay, so these are not simplest of numbers, lots of decimal places. I want you to know that, I believe I have it down a little farther, ln of any value is the same as log base e of that value. There may come a point when this is handy to think about. So ln is simply a logarithm with that base of e. So that's another way to write it. So the inverse of the natural log is e to the x. So if I have the ln of 73, let's go put that in. It's approximately 4.290. Let's go 4 decimal places. I rounded that up from the 5. So if I know the ln of 73 is that, and that this is really the same as log base e of 73, then e is my base. 4.2905 would be my exponent, and that would give me about 73. The ln of 0.25, try that on your calculator, right here. Negative 1.3863, approximately. So if this is log base e of 0.25, then this exponent, I'm sorry, this base e to this exponent. Should be approximately 0.25. Let's go try that one. E to the. And we've done this before. Notice to get e to the second ln. Again, hitting that second button, in a way, well, it shows us that we're using an inverse, negative 1.3863. And we get our 0.25 back, a little rounded. All right. So let's do some of these. Right here, find the natural logarithm. So you know you're using base e, ln of 2.8. What have you got? 1.0296. ln of e squared. All right, that looks cool. ln. How are you going to get e squared? I'm going to press second ln and hit a 2. ln of e squared happens to be 2. Now, how did that work out? Let's examine that one. ln means log base e, and I have log base e of e squared. Log base e of e squared is actually asking me, what exponent do I put on e to give me e squared? 2. Try the ln of 1. ln of 1, log of 1. Whenever you have 1, remember, you're asking what exponent goes on e that gives me 1. So it is indeed 0. Okay, let's jump down a little bit and try something that looks a little more crazy, but really isn't any different. Just like with logarithms, we still have properties for the common logarithms and the natural logarithms. The properties are still in play. So I could actually transform this, a little property practice. ln of 60 to the half minus ln of 10 to the half, and a half is a square root, so I have subtraction as well. How about ln of 60 divided by 10 to the half? This is looking fun. 60 divided by 10 is the ln of 6 to the half. So I'm actually looking for ln of the square root of 6. It's not going to be anything special.
But will those students who are participating in the psychology and the environmental science field trip to the Buffalo Zoo, please report to the horseshoe at this time. Once again, those students participating in the field trip to the Buffalo Zoo, please report to the horseshoe at this time. Thank you.
9 if I round it. Okay, and ln of 25 squared, we can do, bring that 2 out front, 2 ln of 25. Let's type that in to ln 25, approximately 6.4378. So just practice using your calculator. All right, the anti-logarithm. So if we're doing natural logarithms, you can hit second ln to get the anti-logarithm for an ln. So second ln gives me ln inverse, ln of x equals ln inverse of 0.2155. I just inversed on both sides. That reduces it out. And here hit second ln and type in 0.2155. 1.2405. So again, let me do this one 2 ways. You could, to get the x alone, write ln inverse of ln of x, that inverse, cancels those two out. Inverse on the other side, ln inverse of negative 3.8. So all you're going to press is second ln and put in negative 3.8. And I've got, let's go with blue, 0.02237, so 0.0224. The other way to think about this problem, I said I would do it two ways, is that ln of x really means log base e of x, and we have that equal to negative 3.8. So now change this log equation to bend form. E to the negative 3.8 equals my x. And when you hit second ln, that's exactly what you get. Second ln, put in negative 3.8, and you'll get that same answer. So really think about those either way. Little property work. We said the properties are the same for natural logs, common logs, doesn't make any difference. 6 is 2 times 3. So when I'm multiplying, we can split up the logs with addition. Go ahead and put in the ln of 2, close your parenthesis, plus the ln of 3, close your parenthesis. I've got 1.7918, still rounding. Let me check that one again. ln of 2 plus ln of 3. Yeah, we're looking good. ln of 2 divided by 3. ln of 2 minus the ln of 3. Go ahead and type those in. ln of 2 minus ln of 3. I'm still rounding, so that's my rounded value. ln of 64. Well, I know 2 to the 6th is 64, so I'm going to use that fun little fact. So this is really the same as the ln of 2 to the 6th. The 6 comes out front. Properties don't change. And let's do 6 times the ln of 2. And I just realized something. This is 4.1589. These answers are all lovely, except that I had directions, and I did not follow directions. So actually, this is a great exercise. ln of 2 is x, so I'm going to make that x. ln of 3 is y, so I'm going to make that y. This is the answer that I was expecting, and I got carried away. Number 10, ln of 2 is x, ln of 3 is y, so this is x minus y. And number 11, we have 6 times the ln of 2, which is x. There you go. We did them two ways. We did it better. See you tomorrow.